switch the stage. The last important topic in this chapter, atomic structure, writing electronic configuration. Electronic configuration of an atom means how electrons are arranged in spaces around the nucleus in an atom. And what are those spaces? And those spaces are what the term that we are using are orbitals. How in different orbitals, and the concept of orbitals it came around from the wave nature of electron. When we consider that electrons have wave characters, and according to Schrodinger's wave equation, and with the application of Schrodinger's wave equation, is based on an assumption that electrons have wave character, they have wave nature. We are not able to locate the exact position and the velocity of the electron at the same time. The only thing that we can say is the probability of finding an electron, and the places where there is a maximum probability of finding electron are called orbitals. So electronic configuration is how electrons are arranged in different orbitals, and for that we have learned three important principles and rules. For example, the Aufbau principle, the Hertz rule, the Pauli's exclusion principle, which says that only two electrons in an orbital can accommodate only two electrons, which will differ in the spin quantum numbers, with all the three remaining quantum numbers, the principal quantum number, the azimuthal quantum number, and the magnetic quantum number same, that will differ only in the spin quantum number. So an orbital can accommodate a maximum two electrons, which will differ in their spin quantum number. So there are two ways of in the electronic configuration. There are two ways of writing an electronic configuration. Either we use the subshell notation, the SPD notation, or we can use an orbital diagram, which looks like this, which is just the diagrammatic form of this one. And S subshell can contain maximum of 2 electrons, P a maximum of 6 electrons, and D orbitals or D subshells can accommodate a maximum of 10 electrons. This can be diagrammatically drawn like this, like S with single box, P with 3 boxes, and D with 5 boxes. Each box represents one orbital. So this is one orbital of there's one S orbital, there are 3 P orbitals, and there are 5 D orbitals. The 3 P orbitals, they are degenerate orbitals that we use in stating the Hertz rule, which says that the degenerate electrons should be filled with electrons singly. Then after there will be occupation of 2 electrons. First you fill the orbitals with single electron, then pairing will take place. That is Hertz rule of maximum multiplicity. Okay, so let's start with writing electronic configuration of the first element, hydrogen, which is the simplest atom containing only one electron. Its atomic number is 1. So where will the electron go? It will go in the 1s shell or 1s subshell, because in the first shell there is only one possible subshell, and that is 1s, and it can accommodate 2 electrons. So we write the one like this, and if we use the orbital diagram, we'll just draw a box and represent the electron with one upright arrow. Right? So let's go to the second element, helium. The helium the atomic number of helium is 2, which means that it has 2 protons in the nucleus, and in order to nullify the charge, so that the electron as a whole becomes neutral, there will be 2 electrons which carries negative charge, equal in magnitude, but with the opposite charges, negative charges. So there are 2 electrons. This atomic number, what I mean to say is atomic number actually means the number of protons, but it is exactly equal to the number of electrons present in an atom. So since there are 2 protons, there will be 2 electrons. And how are these 2 electrons arranged? The second electron will go to the S orbital itself, because S can accommodate 2 electrons. So it will be 1s2. In the 1s subshell there are 2 electrons, and if you draw the orbital diagram, it will look like this. one box with 2 electrons. These 2 electrons, they differ in their they have three three quantum numbers same. The fourth quantum number, the spin quantum number, one will have plus half clockwise, and then another it will be having minus half. That is spin is anti-clockwise. Okay, the third atom is lithium, atomic number 3. That means there are 3 electrons. Now the 2s orbital is filled up. It's according to Pauli's experiment principle, an orbital can have a maximum of 2 electrons. So the third electron cannot be accommodated in this. It will go to the next orbital with the greater energy. So it is 2s orbital or 2s subshell. So the third electron, after filling up, there are 3 electrons, right? 2 electrons will fill up here. Third electron will go to the second shell or second subshell or second orbital, 2s1. So this is a 2, this is a third electron, right? So what about beryllium? In case of beryllium, there are 4 electrons. So the fourth electron, after first, second, third, the fourth electron will still be filled up in a 2s orbital or 2s subshell. So this is the fourth electron. So this was the electronic, either you write the electronic configuration of beryllium like this, which we call subshell notation, or you can write as orbital using orbital diagram. But what is the advantage in writing the orbital diagram? In writing the orbital diagram, we can show all the 4 quantum numbers, because when you're putting 2 arrows upside and upright and inverted arrows, it indicates the spin quantum number, right? So all the 4 quantum numbers are being shown when we use the orbital diagram. That's the advantage of using orbital diagram. It makes the picture clearer. Okay, then boron, there are 5 electrons, so 1 is 2. Here also 2, 4 electrons. The 5th electron will now 2s subshell is now filled up, because s orbital can accommodate only 2 at the maximum, so it will go to the p orbital or the 2p subshell. So 1, 2, 3, 4. The 5th electron will go to the p subshell. These three orbitals are degenerate orbitals having the same energy, 2p, 2p, 2p. One is 2px, one is 2py, and one is 2pz. But their orientation are different. We were not talking about orientation when we were filling up the 1s orbital and 2s orbital, because s orbital is spherical. There is no point of saying the direction or orientation, because the value of m is 0. But when it or because the value of L is 0. When the value of L becomes 1, there are 3 possible values of M. That is 3 possible orientation, which is the magnetic quantum number. So there are 3 orbitals. These 3 orbitals, although they are in of same size, same shape, and same energy, that's why they are called degenerate orbitals. Their direct orientations are different. Now let's see the next atom, nitrogen atom, atomic number 7. So there are 7 electrons. How will this be filled up? 1 is 2, the first subshell is filled up, the second subshell is filled up, 2 is 2, 4, 5, 6, 7, 3 more electrons are left. So how will it be filled? It will not be filled like these are 3 orbitals, 3 different subshells, 3 different subshells available, 3 different orbitals are available in 2p subshell, right? So it would not be filled. Pairing will not take place. First you make them fill singly. First the orbitals will be singly filled. That is what the Hund's rule say. Hund's rule says that when electrons are going to fill up in degenerate orbitals, it should be filled singly first, then only pairing will take place. So after filling up singly, so there will be 3 electrons in p orbital. P orbital can maximum accommodate 6 electrons. So first make the orbitals fill up singly, right? So the electronic configuration of nitrogen, although here we are not able to see the picture clear, but when it comes to the orbital diagram, when we use orbital diagram to write the configuration, we're able to see that the 3 electrons in a 2p subshell are in different orbitals, different 2p orbitals. These 2p orbitals have different orientation. They are dumbbell in shape p orbitals, and they have different orientation, one in the x-axis, one in the y-axis, and one in the z-axis, right? You can imagine like that. Hope it's clear. Okay, what about this one? See, if someone says that, well, what will be the 4 quantum number for this electron, right? it is in the first shell. So the principal quantum number is 1, n equal to 1, and since n equal to 1, there is only one possible value of L. It is 0. That means shape of the orbital is S, so it's 1s. Since L equal to 0, the only possible value of magnetic quantum number is 0, so that means it has no orientation, right? And for this, S equal to plus half, or it may be minus half too. What about this electron? If someone says that what are the 4 quantum numbers for this particular electron, how will it do? This is 1s, 2s. This is 1s orbital, this 2s orbital. So that means the value of n equal to 2, L equal to 0, because still S, right? If n equal to 2, there are 2 possible values of L, 0 and 1. 0 means S, right? So it is L equal to 0. Since it is S orbital, 2s orbital, L equal to 0. Since L equal to 0, the value of M is, the only possible value of M is 0. So value of M equals 0. And what about the spin quantum number? It may be taken either plus half or minus half, right? So in this way, by just looking at the orbital diagram, you can say the 4 quantum numbers for that particular electron. Hope you are understanding the things.